Hello friends, let's see today polystyrene plastic. So in this unit you will learn about all the plastics which are based on styrene. Styrene is produced from ethylene and benzene in the presence of aluminum trichloride as catalyst at 600 degrees Celsius. Industrial production is preferred by free radical polymerization using suspension or bulk technique. Mostly produced as a atactic material and hence poor crystallinity. So you know the tacticity of polymers, tactic, atactic and syntactic, right? Now benzene, when reacting with ethylene, benzene ring plus CH2 double bond CH2 giving you ethyl benzene in the presence of aluminum trichloride as catalyst. Then this ethyl benzene gives styrene and H2 is liberated. Then polymerization leads to the formation of polystyrene. Also FeO and MgO is used here and 600 degrees Celsius is there. Then you polymerize this monomer styrene and you get, by bulk or suspension technique, you get polystyrene. So always remember that while writing the monomer there should be a double bond, and when writing the polymer it should be a single bond, but it should be extended chains at the end here, and this should extend here also, and end time signifies that this is a polystyrene molecule, or this structure is also correct, and this means that the chain extended from this side only. Now application of polystyrene. Manufacture of molded articles like containers, jars, bottles, television cabinets, toys and household items. Manufacture of optical plastic component because of high refractive index. So you must have heard that many optical glasses are made by polystyrene. It is because of its high refractive index. As an insulating material also it is used. Piping, automotive interior parts, food trays and cups. Thermal degradation or depolymerization is possible along with many low molecular weight compounds. Poor solubility in organic solvents, poor weathering properties and brittleness, yellowing and crazing of the polymer, low heat distortion temperature. So now what is low heat distortion temperature? So first you have to understand what is heat distortion temperature. It is one heat resistance index. It is an index of strength of the material at high temperature. Means suppose you have a polymer and you keep it in a hot solution and you keep a load over it, so at some time it will resist the load, so the polymer will maintain its dimensions, but once the temperature goes beyond its heat distortion temperature, then definitely the polymer will show the bend, and that is why it is the heat distortion temperature. Though the thing he's saying is that the one of the property, it's low, it has a very low heat distortion temperature, that polystyrene gets distorted at a very low temperature. That may be a negative point, but usually it does not happen till 60 degrees, so temperature in the room, in the atmosphere, does not go above 60, so it's good. Styrene, maleic anhydride. Styrene and polystyrene were first introduced in 1938 for general application, hence known as GPPS, means general purpose polystyrene. Since high brittleness and low glass transition temperature were the biggest disadvantage, as I said, for polystyrene. To impart the slightly higher heat distortion temperature, copolymerization with maleic anhydride were tried to produce styrene maleic anhydride. So you see, that's why we have to add some copolymer to improve that bad property of polystyrene. So we took styrene, we take maleic anhydride, which is nothing but CH double bond CH, CO2, O. Then copolymerize it and we get styrene maleic anhydride. So just take this entire molecule and paste it here. CO2O, CH and CH. The double bond is getting converted to single bond because it is a polymer now. Application was suited to a slightly improved material as compared to polystyrene. Styrene butadiene rubber. Production started in the US in the year during the Second World War. Initially identified as cold rubber by solution polymerization with suitable catalyst. So the the Second World War was between the Nazis and the Allied forces. So US, Allied forces were demanding weapons from the US. So US was constantly improving, inventing new things. So they invented the cold rubber by solution polymerization with suitable catalyst. So that was the initial beginning of the SBR. Improvements were made in polymerization temperature and addition of active initiators. By virtue of free radical polymerization, SBR is a random copolymer and hence irregular structure. So this was earlier done by solution polymerization. Then some improvements were made. The sturdity of SBR is strictly dependent upon the number of butadienemers involved in the SBR structure. So more the butadiene, more the sturdity. The final product depends on processing of SBR up to certain extent. So styrene 75%, butadiene 25% copolymerization gives styrene butadiene rubber. Properties. Interior strength as compared to natural rubber, but at elevated temperature they are quite comparable. The ozone resistance of SBR is superior to that of natural rubber, but when cracks or cuts starts in SBR they grow rapidly. Heat resistant and tough up to certain extent, along with better weatherability and natural rubber. So heat resistance is also improved as compared to natural rubber. Ozone resistance is also improved, and interior resistance is also improved. Application. Cold SBR is used for light duty tires, mostly appreciated for many mechanical objects due to their easier processing and good quality end product. Such items are belt, molded good, unvulcanized sheets, gum and flooring. Manufacture of shoe soles and for coated fabrics. For electrical insulating material. So you can see there are so many uses of SBR. High impact polystyrene, HIPS. Basic concept of high impact polystyrene or polystyrene molecules. HIPS is made by dissolving styrene butadiene rubber in styrene, then polymerizing the same via bulk polymerization or suspension technique. So how HIPS is made? Dissolving styrene butadiene rubber SBR in styrene and then polymerizing the same via bulk or suspension. Initially the styrene and the butadiene are polymerized by emulsion technique, and their latex solution is then mixed with styrene and allowed to get polymerized. Styrene, SBR latex, bulk or suspension giving you HIPS. So this is done by the emulsion, then you add styrene, then you do bulk or suspension, you get HIPS. So now HIPS is even better in quality. Like high impact polystyrene materials are the important modification in the polymerization reaction of styrene, where the various co-monomers like butadiene, acrylonitrile, mixture of acrylonitrile and butadiene and maleic anhydride are introduced, which improves the heat and impact strength of the polymer without the loss of the desirable properties. The typical comonomer increases the intermolecular forces of attraction by introducing polar groups, which stiffens the chain and reduces the rotational freedom through the steric hindrance of bulky side groups. So rotational freedom, this concept you will learn in 5th semester, so don't bother about it right now, just learn this. Typical examples are styrene, butadiene, rubber up to a certain extent, toughened polystyrene, styrene acrylonitrile, acrylonitrile butadiene, styrene, styrene maleic anhydride. The ratio of X to Y decides the impact strength of HIPS. The impact strength of HIPS is improved up to 7 times as compared to SBR or polystyrene material, but the tensile strength, hardness and softening point reduces. So even though the impact strength of HIPS is 7 times as compared to SBR, but the tensile strength, hardness and softening point reduces. The use of stabilizers may sometimes create adverse impact on the cross-linking of rubber. Hence, it should be added in later in stage when the rubber has reached a moderate degree of cross-linking. So you don't use the stabilizer early on, you use them later on. Okay. Applications of such materials are based upon the high impact strength and high resistivity required. So wherever there is high impact strength required, high resistivity required, we use HIPS. Example: internal automotive parts of vehicle. Exactly, because the car get crashed, the material should sustain the shock, so we use HIPS. The most important uses are in food packaging, since it can easily thermoform to form cups, plates, etc. Now you see the comparison table here: tensile strength, elongation and impact strength. Polystyrene 4000 psi, HIPS 3500. As he said, tensile strength reduces, elongation is increased, impact strength is increased. Toughened polystyrene plastic, TPS. The concept of toughening due to microstructure PVD, polybutadiene. The impact strength of brittle plastics such as polystyrene can be significantly improved by incorporating a rubbery phase by polybutadiene in the form of small dispersed particles, provided that the adhesion between the dispersed phase and the matrix polymer is good. Sometimes the HIPS mixture, which is nothing but PS plus rubber particles, can also be blended after polymerization with polyphenylene oxide to improve toughness, heat and chemical resistance. So what is HIPS? Styrene plus SBR latex. So he calls SBR latex as rubber particles. The rubbery phase mixed with polystyrene when irradiated with UV may also toughen the PS, polystyrene. Because the rubber particle can provide an energy absorbing capability through a change in mechanical deformation proceeds. Major applications are in making ion exchange resins, pressure sensitive adhesives, soft contact lenses, controlled release of drugs, preparation of novel membranes, and vibration damping material. Styrene acrylonitrile copolymer. So now, SAN. Acrylonitrile is commonly called as vinyl cyanide, CH2 double bond CHCN. The triple bond nitrogen produces very strong dipole bonding between neighboring molecules. Resulting a high melting point and viscosity. So this is a triply bonded nitrogen, CN, C triple bond N, and produces very strong dipole between neighboring molecules, resulting in high melting point and viscosity. Due to this, it is very difficult to mold. Hence, to improve its moldability, it is usually copolymerized with 20% polystyrene. Since it has like this strong dipole bonding, so its viscosity is very high, so it is very difficult to mold. Hence, to improve its moldability, it is copolymerized with polystyrene, 20%. As the percentage of acrylonitrile increases, the strength increases and the moldability decreases. Because of the strong polar nature of acrylonitrile molecules, the copolymers have better resistance to hydrocarbons and chemical inertness. The toughness is due to the higher content of acrylonitrile, and so does the yellowness. Since rigidity and transparency is the characteristic feature of this polymer, and hence it is very important to maintain the percentage composition of both. 20% styrene, 80% acrylonitrile, that is vinyl cyanide. Copolymerization gives you sand. Properties of sand: high rigid material, tough but equally moderate transparency. Improved resistance to oil, hydrocarbons and chemicals. High softening point as compared to acrylonitrile. High impact strength due to strong intermolecular forces. Applications of sand: preparation of dials, knobs and covers for domestic applications, electrical equipment and car equipment. About 10% of sand goes for packaging of cosmetics and pharmaceuticals. Also in the preparation of various molded items where the thermal stability is a prime requirement. Now blending of polymers. Butadiene 65% with nothing but CH2 double bond CH double bond CH2. Acrylonitrile copolymerization give you acrylonitrile butadiene. Then acrylonitrile styrene copolymerization gives styrene acrylonitrile. Blending the 1 and 2, that is the acrylonitrile butadiene and styrene acrylonitrile, giving you acrylonitrile butadiene styrene. Normally 60 to 70% of sand and 30 to 35% of butadiene, giving you ABS, that is acrylonitrile butadiene styrene. Copolymerization. Here you take butadiene, polymerization give polybutadiene latex. Polybutadiene gives you styrene plus acrylonitrile. Copolymerization, X and Y are variables giving you what? ABS, acrylonitrile butadiene styrene, where A represents butadiene chain, B represents sand. So actual representation is like this. This is the sand molecule, this is the butadiene chain, this is again the sand molecule. So first it was formed by blending, then it was formed by copolymerization. Now polymerization technique. Here butadiene molecules are first polymerized using emulsification to get polybutadiene latex, and then styrene and butadiene are added to it. The mixture is warmed at 50 degrees to allow absorption of monomers in the presence of potassium persulfate as an initiator, especially to polymerize styrene and acrylonitrile. The material consists of two phases: glassy matrix of sand and rubbery solution of acrylonitrile butadiene, and essentially insoluble in each other. To increase the strength of bonding between the two phases, sand side chains are grabbed to the main chains of butadiene. The rubbery phase is interspread with sand particles, producing a complex microstructure. The size, concentration and distribution of the rubbery phase can vary widely between grades, which is typically 50 micrometer. Acrylonitrile butadiene styrene. Need for production of ABS plastic. It is commonly produced in tubes. Blending of acrylonitrile styrene copolymer with butadiene acrylonitrile rubber. Second, styrene and acrylonitrile are added to the polybutadiene latex and heated at 50 degrees Celsius. So the two methods I have explained you already. Applications of sand. Typical blend consists of 65 to 35 or 70 to 30 ratio, where 70 parts sand and 30 parts butadiene acrylonitrile rubber. By altering the variables in the blend, we may get final product of various impact strength, processability, toughness, low temperature and heat resistance. Example, a blend of 65 parts styrene acrylonitrile and 25 parts of nitrile rubbers and 10 parts of butadiene will increase the toughness at low temperature. It is observed that for producing high impact materials, the sand should have high molecular weight. Normally 15 to 20% acrylonitrile is required to improve the toughness of material. The commercial copolymers containing 20 to 30% acrylonitrile are suited for the preparation of ABS polymer. Properties of ABS. Combined toughness due to rubbery phase. Chemical resistance due to acrylonitrile terminals. excellent moldability due to polystyrene, high impact strength due to sand, poor flame resistance about 200 Fahrenheit, high adhesion property due to strong intermolecular forces and grafting, poor weathering resistance and lack of transparency. In the manufacture of pipes, fittings, especially drain water and wastewater. In instrument and appliance housing, electrical screwdrivers and automotive instrument parts and panel, video and computer parts. For electroplating agents, especially chrome plating. In the manufacture of luggage bags, suitcase, motifs, car bodies, etc. In the adhesives. So this is adhesive. This is the ABS. So ABS is quite complicated. So till SAN you will understand, but you have to give extra stress on the ABS. So acrylonitrile butadiene styrene. So the major applications of ABS plastic sheets include refrigerator industry, 3D building material, machine prototype constructions, pipes, fittings, vacuum constructions, keyboard keys, power tool housing, automotive industry. Because ABS plastic is much lighter than other plastics, vehicles that use ABS and plastic that are similar to ABS can decrease the weight of the vehicle by 10%, making them more fuel efficient. Typically, ABS sheet is used on dashboards. So whenever you think whatever the dashboard of the car is made up of, it is made up of ABS plastic sheets, wheel covers and body parts because of its strength, low temperature resistance and rugged surface that don't easily get scratched. So this is all regarding the unit number 5. I hope you understand.